Okay, so I guess we can move into the asking, do people have specific questions?
While we wait for some questions to pop up, we have PyLith 2 version 2.1 comes with the custom fault preconditioner ML and LU. It does not come with mumps or super LU. If you want those and want to experiment with those, you need to build PyLith from source. We have found that ML works quite well. We in 3D examples 3D Tat 4, we show in step O2 how to use ML when you don't have a fault, and in step 4 we show how to use ML when you do have a fault. I believe we also have a couple other examples, perhaps in 2D subduction where we use the ML. Uh, that's the algebraic multi-grid preconditioner. We don't have any examples other than what Matt showed using the Sure complement. Part of that is that when it came down to some of the tests we've done, in terms of runtime, the ML with our custom preconditioner generally gave the fastest runtime, but there's still some additional sort of parameter choices that we haven't experimented with. As Matt showed, there's a lot of sort of fine tuning. You can back off one tolerance here or there in the inner or outer solve to try and optimize your runtime. And that's generally what everyone cares about, is the actual runtime rather than how many iterations it actually takes.
Right.
So and as Matt suggested, if you do have questions about the solver, send in emails, because oftentimes it does require a little bit of interaction with Matt to fine tune the solvers, because there really is no black box. One solver works best for every type of problem.
Yeah. And I guess I can also say that the coming up, what we're looking at, I, I expect in the spring, although it would be great, if it was slightly before that, is that we will have multi-level solves in PyLith. The real way to do the whole thing is to have a nonlinear multigrid where we solve the full PyLith problem on each multigrid level, and we have all the tools to do this, but putting it together for a real problem is quite different than putting it together for a test problem. So I showed plenty of test problems where this works wonderfully, but a real problem you have to get all of the boundary conditions right and make sure all of the data shows up correctly on the course levels and stuff like this. And that's the challenge for us right now. But I believe in the spring it should all be ready to go.
I see some evidence of typing, but no question yet. Are there other questions?
And it's fine to ask on any aspect of this, the solvers or how will it run in parallel or something like that. Because this is really this is the performance unit. So anything you want to know about that. We can look, I think, after lunch, or depending on where you are after lunch, we are going to talk about debugging.
That's right. There'll be a few slides on sort of debugging strategies, and then the rest of the time, there are examples where we've intentionally put some errors to show the different types of errors that are most common. and we'll look at the error and do fixes to find out what those problems are. I'll admit I haven't looked at those errors in a year, so we'll see.
Yes.
Okay, Matt.
Okay, you want to find the minimum Jacobian in Petzius.
That's the Jacobian cell.
That's the Jacobian what? I
Error
don't.
message
There.
then a minimum is for the Jacobian mapping the actual cell to the reference cell geometry. So that is
Oh, yes.
related to the solver, but actually the non-dimensionalization scales. So if you generally you want your length dimension to be on the dimension of an edge of a cell, and so the default is a kilometer. And so if you have a domain that has things that are much smaller than a kilometer, you will want to update your scale appropriately, your length scales appropriately.
Yeah, and just let me clarify. Jacobian is being used in two different senses here, or referring to two different things, I guess I should say. The Jacobian in general is the tangent to some nonlinear map, right? So it's the derivative in some sense, if you want. And so there are two maps here. One map takes real cells and maps them to a reference cell. And we do finite element computations on the reference cell. The other Jacobian is the Jacobian of your equations, your nonlinear map f of x equals 0. So the minimum Jacobian that is being talked about there is the minimum determinant of the Jacobian of the mapping from a real cell to the reference cell. And the determinant of the Jacobian there gives you the volume of that cell. So, and what it's saying is the volume of your cell is very, very small compared to the reference cell, and so you're not going to be very accurate. And as Brad said, that usually arises from and kind of a non-dimensionalization, which is very far from your problem scale.
Any other questions? There are a few dynamic rupture examples available in, let's see here. I think yes, examples bar shear wave. We try and keep our examples that are included in the distribution small. Most real sort of seismologically interesting dynamic problems require running on a cluster, and so the meshes tend to be very, very big, so we don't include those in the distribution. There are a number of dynamic rupture benchmarks that have been run with PyLith, and they are included. There's a link, there's a separate repository for those files. They do not include the meshes, and you'll find a link to those, that Git repository in the manual. I think they're called PyLith benchmarks is the repository on the CIG website. Any other questions? Well, it doesn't look like we have any other questions right now. If you do have questions, feel free to, in the coming sort of hour or so, feel free to put them in the Q&A pod there, and we'll answer them. And if you have we should have plenty of time in the next session for your final questions as we wrap up the tutorial in a few hours. So we'll see you back again at 1 p.m. Pacific time.
Thank you very much.